Every object has its own rhythm. We call this the natural frequency. What happens if the rhythm of an external force matches the object's natural frequency? In this video, we will learn about resonant frequency. Let's use a swing as an analogy. We will call the natural frequency I mentioned earlier the rhythm of the swing. The swing is moving. At this moment, someone is pushing the swing from behind. This is the external force I mentioned. They are pushing exactly when the swing goes down. Even with a small force, the swing goes higher and higher. The resistance is in a minimum state. In a circuit, the resistance is in a minimized state. In a circuit, this state where resistance is minimized is similarly called resonance. Conversely, what if the timing of pushing the swing is too fast or too slow? If it's too fast, collide with the returning swing, and the energy cancels out. In a circuit, this is a state where the frequency is higher than the resonant frequency, blocking the energy. Also, if it's too slow, you miss the timing to push the swing. In a circuit, the frequency is too low, so the energy is not transferred efficiently. Resonant frequency uses the following formula. Here, L stands for inductance and C stands for capacitance. To make it easier to understand, let's look at a RLC circuit together. This is a function generator. This component plays the role of the person pushing the swing. The 100 mH inductor represents the swing's weight. The 100 microfarad capacitor represents the swing's height. Its voltage rating is 16 volt. If we plug this into the resonant frequency formula, we can see that the resonant frequency is about 50.3 Hz. I have placed the function generator to create the frequency and an oscilloscope to check the input and output frequencies. I set the input frequency to about 50 Hz. The voltage is 5 volt. As the resistance approaches zero, you can see the waveform on the oscilloscope growing rather up and down. Conversely, here's a case where the timing is too fast. I set the input frequency to about 200 Hz. Since the frequency is higher than the resonant frequency, the waveform becomes smaller. It is hindering the flow of the circuit. This time, here is a case where the timing is too slow. I set the input frequency to about 10 Hz. The amplitude of the waveform appears very small. This is a case where the force is not being transferred. Thus only the amplitude increases when it matches for resonant frequency. Let's check the voltage after applying a frequency of 50 Hz. The voltage keeps increasing. We call this voltage rise. It is the same as energy accumulating when pushing a swing. This can cause capacitor destruction and damage to ICs or circuits. The efficiency in a resonant circuit is expressed as the Q factor. The Q factor gets larger as the circuit's frequency gets closer to the resonant frequency. This means that because the efficiency is good, a larger amount of energy can be accumulated. The Q factor can be expressed by the following formula. The smaller is resistance, the larger the Q value. Let's reduce the resistance value to 1 ohm. You can see that the voltage increases beyond the input voltage, destroying the capacitor. Now I will raise the resistance value back to 20 ohms. The capacitor is not destroyed and the waveform is output normally. To prevent this voltage rise, you can solve it by increasing the resistance value of the circuit. We call this process damping. In this video, we will learn about resonant frequency, Q factor, and damping. If your video was useful, please press the subscribe and like buttons. Thank you for watching.